We're in sort of a strange situation with matrices. On the one hand, we have these matrix operations that we defined sort of using linear vector functions as our inspiration. So these are matrix addition, matrix multiplication, and scalar multiplication. On the other hand, we have these row operations that we do on matrices mostly to solve systems of linear equations. And the row operations, they don't seem like they're really related to the matrix operations in any way. And that's sort of a strange situation. And so we're going to fix that situation. What we're going to try to do is kind of embody the row operations as matrices. So before we can do that, though, we need to notice something about matrix multiplication. So let's multiply out. So we're going to multiply this matrix A on the right by C. So we're going to work out A times C. And so the first column of this product, the way that we usually do this, or the way that I've suggested that you do it, is by taking the first column of C and sort of tipping it on its side and setting it above the rows of A, and then sort of sweeping it downwards, and you do this product sum thing as you go. So 3 times 1 plus 4 times 2, so that's 11. And then 3 times 3 is 9, plus 16 is 25. And then 15 plus 24 is 39, I guess. Okay. But notice that what happened here is this first column of the product is actually, it's 3 times the first column of A, so 1, 3, 5. In fact, since this 3 is coming from C, let me write it on the right like this. So it's 3 times the first column of A plus 4 times the second column of A, which is 2, 4, 6. Right? And then if we work out the next column of A times C, so that's going to be we're going to use minus 2 and 5. So minus 2 times 1 plus 10, so that's 8. And then minus 6 plus 20 is 14, sorry. And then minus 10 plus 30 is 20. Okay. And this second column of A times C, this is negative 2, so this negative 2 coming from C, times the first column of A, 1, 3, 5, plus 5, and this 5 is coming from C again, times the second column of A, so 2, 4, 6. So what we're seeing here is that when you multiply on the right by a matrix, another way to think about what's happening is that the columns of the factor on the right sort of act as coefficients multiplying the columns of the matrix on the left. So really we're sort of, it's almost as if we're treating the columns of A as vectors in their own right, and we're combining these vectors using coefficients from the matrix that's on the right, which is C in this case. So matrix multiplication viewed this way is sort of combining the columns of A using coefficients from C. Okay, that's fair enough. It turns out that although that will be useful for us in the future, it's not so useful now because, remember, we were talking about row operations. And you can see what's happening here is we're kind of doing column operations, right? We're multiplying columns by scalars and then adding columns together. That's kind of like a row operation, except it's with columns instead of rows. So let's do this whole exercise again, but let's multiply the matrix A on the left by something. So let's multiply A on the left by B, so like this. So let me actually write A over here. It's a little tricky to do this multiplication with the matrices spread all over like this. So 1, 3, 5, 2, 4, 6. Excuse the cats in the background. So we could use the columns of A and sort of tip them sideways and sweep downwards through B. But there's another way to think about what's going on here. We could instead take the rows of B and set them vertically like this. So taking the first row of B, it would be 2, 1, 0, and then sweep it sideways across A. And we do the same sort of multiplication and adding as we go. When we do this, we're going to get, well, since we're moving rightwards, we get the first row of the product instead of the first column. So 2 times 1 is 2, plus 1 times 3 is 5 total. So, and then 0 times 5. So 5, so that's 2 plus 3. And then when we move over to multiply these coefficients by these entries, we get 4 plus 0, so 8. So notice that using the first row, we got the first row of the product. Okay, now we can do the same thing with the second row. Right, so now we use 0, minus 1, and minus 2. So then we get 0, minus 3, minus 10, minus 13, and 0, minus 4, minus 12, so minus 16. Okay, so this first row, this was the first row of B, so times the rows of the matrix A. So the first row was 2, and then, sorry, the first entry in the first row of B is 2 times the first row of A, so that's 1 and 2, plus the second entry from B, which is 1, second entry from the first row of B, which is 1, times the second row of A, so 3 and 4, and then the third entry of the first row of B, 0, times the third row, 5, 6. Right, so that all of this is what is giving us this first row. And then the same thing happens with the second row of B times A, except the coefficients are coming from the second row of B. So in this way of setting it up, instead of the coefficients coming from the right-hand matrix and the columns coming from the left-hand matrix, we have coefficients coming from the left-hand matrix and the rows coming from the right-hand matrix. And you can see that these are actually the row operations. Here's scalar product of a row, and here's adding 2 rows together. We'll have to think about how interchanging 2 rows works. But the idea here is that by multiplying the matrix A on the left by B, B is somehow doing row operations. That's the idea here. So what we're going to do is try to express all of the row operations as multiplication on the left by some matrix. And the trick will be figuring out, well, what matrix? So what matrix does what row operations? So here's an example. So suppose we want to interchange the first and the second rows. So this is the matrix whose rows we're going to interchange, and here is the result of this row operation. You can see I've just switched the first and the second rows, but the idea is we should be able to make this switching of rows happen by choosing an appropriate matrix to multiply by on the left. And again, it is important that it's on the left because we're doing row operations. If we multiplied on the right, we'd get column operations. Okay, so remember that along the first row of this matrix are coefficients for the rows of the second matrix. Well, for the resulting first row, we want the second row. So we need to choose, we don't want, right, this entry here is going to multiply the first row, but we don't want any of the first row as a result. So we want a 0 here. What we want is just, in our new first row, we just want a single copy of the old second row. And this is this entry right here is going to act as the coefficient for the second row. So we want a 1 right there. So we get 1 copy of the second row in the first row. And of course we don't want any of the third row, so we should have a 0 here. For our new second row, we want just 1 copy of the old first row, and the entry in the first row that acts as the coefficient for the first row on the right, is this entry right here. So we want a 1 here, and then we don't want anything else, so 0, 0. And we don't want to change the third row at all, and so we should just copy the third row, and the entry here that corresponds to the third row is that entry, so that should have a 1 in it, and zeros here and here. So this matrix, 0, 1, 0, 1, 0, 1, 0, 0, 1, sorry, this right here should be a 0. This matrix, when you use this matrix to multiply on the left, this matrix switches the first and the second row. So there, in some sense, this matrix is the row operation. So we've rephrased switching rows as multiplication by a matrix. Of course, you know, in this particular example, we had a very specific size of matrix that we started with, and so that causes us, you know, since we had 3 rows to begin with and 3 rows to end with, we needed to have a 3 by 3 matrix for our row operation. In general, if you have some matrix that's m by n, and you want to do a row operation that switches 2 rows, let's say the ith row and the jth row, okay, you're going to end up with a new matrix, I don't know what to call it, you're going to end up with a new matrix that's still m by n, right? Row operations shouldn't change the number of rows and the number of columns in a matrix. So to do this row operation by multiplying by a matrix, we'll need a matrix that's, right, for this product to be defined, we have to have m columns here, and to get m rows as a result, we need m here. So we're going to have a square matrix, right? The point of this is this permuting rows like this, switching rows, will be multiplication by a square matrix, no matter what size matrix you started with. And you can see that this square matrix, it's actually just the identity matrix, but we've switched the first and second rows. And that actually always works. To switch the I and jth rows, you're going to just take the identity matrix, but there will be 2 spots that are switched somehow, like this. Okay, zeros everywhere else. So, you know, if we wanted a 4 by 4 matrix to switch row 2 and row 4, right, we're leaving row 1 alone, so a 1 there. We're switching row 2, so there won't be a 1 here, so I'll write a 0. We're leaving row 3 alone. We're changing row 4, and then the 1 that should be here in this 0 spot jumps down to row 4, and the 1 that used to be there in the identity matrix jumps up to row 2. So this is a 4 by 4 matrix that switches the second and fourth rows. Okay, and you can see for any square size and any pair of rows, you can come up with a matrix that switches rows like this just by matrix multiplication. All right, so that's interchanging rows. The next row operation that we should look at is multiplying a row by a scalar. So here we have a matrix. Let's imagine that we wanted to multiply the second row by 3. So this would be the resulting matrix on the right. And, you know, we know that in each row of this matrix on the left, first of all, it has to be square again. And it's 2 by 2 since our starting matrix is 2 by 3. Our result has to be 2 by 3. And so this had better be 2 by 2. For the first row, well, we don't want the first row to change at all, so we want 1 copy of the first row and 0 copies of the second row. And then for the second row, in our result, we want 0 copies of the first row and 3 copies of the second row, so put a 3 here. So the matrix that does this row operation is 1, 0, 0, 3. All right, you can see that this is just the 2 by 2 identity matrix with the second row multiplied by 3. right? Which is the operation that we wanted to do. So, you know, we can embody any scalar or any multiplying a row by a scalar row operation just by using the same trick. So if we want a matrix for multiplying row, say, so let's say it's a 4 by 4 matrix, to multiply row 3 by negative a half, we would just take the 4 by 4 identity and then multiply the third row by minus a half. So there's zeros everywhere else in the third row, but in this third position, just replace this plus 1 with minus a half. And this is the matrix that, when you multiply on the left by this matrix, performs this row operation. Okay, the last row operation is adding one row to another. So let's suppose we want to add 2 times the second row to the third row. So for the first row in our result, we want 1 copy of the first row and then no copies of the second and third row. So 1 copy of the first row and no copies of the second and third row. We aren't changing the second row, so the coefficients for the second row on the left should be, right, no copies of the first row, 1 copy of the second row, and no copies of the third row. But for the third row, down here, we don't want any copies of the first row, right, because we're adding 2 times the second row to the third. So we want 2 copies of the second row, so we need a 2 here, so that when we do this multiplication, this 2 that I just wrote down is going to sweep across the second row of the matrix on the right. And we want to add that to the third row, so we also need 1 copy of the third row, so we need a 1 right there. And so this 3 by 3 matrix will do this row operation. All right, and as usual, you know, it's pretty easy to figure out a matrix that will do any of these row operations. So if we want to add, just to pick another one, let's say we want to add minus 4 times the third row to the first row. Okay, and let's say again this is a 4 by 4. We're looking for a 4 by 4 matrix operation. We can take the identity matrix that's 4 by 4 and then add negative 4 times the third row to the first row. So doing that just takes this 1, multiply it by minus 4, and add it to the first row, so that puts a minus 4 right here. You can see this matrix that we got in our first example, that's just the identity matrix, the 3 by 3 identity, but then you add 2 times the second row to the third row, that puts a 2 right there, which is what we got, right? But so so what we're seeing here is by starting with the appropriate square identity matrix and then doing the row operation that we want, what we get is a matrix that does that row operation when you multiply on the left by that matrix. All of these row operations, they really are just matrix multiplication, but by special matrices. So these matrices that embody the row operations, they're called elementary matrices. And they sort of come in 3 flavors, right? They're all square, but there's the row swapping flavor, which looks like this. There's the scalar, multiplying a row by a scalar matrix, which looks like this, right? And which row gets multiplied by the scalar depends on what position that scalar is in. And then there's the matrices that add a multiple of a row to another row, which looks like just ones down the diagonal, but then off the diagonal there's some entry somewhere, some scalar. And what the position of this scalar is determines which row gets added to what other row.